assignment in the disk. So each one, everyone should get one. So first I will explain the assignment. So the due date is March 16th. So it should be Thursday next week. So next week when we come here, you should turn in your assignment. So this assignment has two problems. The first problem, a converter has a single AC voltage input. So you can see Vin, it is AC, and the frequency is 60 Hertz. And the amplitude is Vin. We have two switches, switch 1 and switch 2. When switch 2 is on, the output is short circuit. So if switch 2 turn on, then the output is 0. And if the switch 1 turn on, then the output is equal to Vin. So the switches operate so that Q1 plus Q2 equals to 1. So you can see Q1 plus Q2, you can get 1. A, please draw the circuit which includes power devices. So what kind of power devices will you use? Will you use diode? Will you use MOSFET? Will you use IGBT? Will you use power transistor or another? So you have to show your power device and the circuit. So this is problem A. B, the frequency of the input is 60 Hertz. The peak value of the input voltage is VO. And the frequency of Q1 is 10 kHz. So Q1 frequency is 10 kHz. The output average power is PAVE. So the problem gives you certain condition. So the question is, what is the amplitude of the 60 Hertz for a component of the input current In? So what is the amplitude of fundamental? Fundamental is 60 Hertz In. So the In is not a value, it is a relationship. It could be related to VO, it could be related to PAVE or anything. So it is not a value, it is an equation. So you have to develop the relationship. So this is problem 1. So do you have any question about problem 1? Okay, then we can move to problem 2. An AC to DC converter is shown in figure 2. I out is a constant, so we have constant output current, and it is positive value. This is an 3-phase AC to DC converter. The switching function of the ideal diode is if I switch current larger than 0, then the diode is turned on. If the V switch less than 0, then the diode is turned off. So we have 3 diodes. We call SA, SB, and SC. So we use 3 diodes to do the 3-phase AC to DC converter. Okay. So if the diode is turned on, it means the current is positive. If the diode is turned off, which means the voltage across the diode is negative. So VA equals to VO cosine omega t, VB equals to VO cosine omega t minus 120 degrees. VC equals to VO cosine omega t plus 120 degrees. A, please plot V out. So you have to plot VA, VB, and VC, then you can plot V out. So first, plot VA, VB, and VC. Then you can plot V out, which is related to VA, VB, and VC. B, please compute the average of the V out. C, sketch the switching function of the switch SA. So you have to draw VA, VB, VC, and also the switching function of SA. So do you have any question about problem 2? It is 3-phase AC to DC converter. We call it is half-wave rectifier. Half-wave rectifier. So do you have any question about problem 1 and problem 2? So if no problem, then you can spend some time to finish the assignment, and next Thursday when we come here, please turn in your assignment. So now we will continue to, so please get one assignment here. So now we will continue to the chapter 1. So we will finish chapter 1 today. So now we have the final example. So we have S11, S21, S12, S22. We have 4 switch. So here we can get V1, here is V2. So V1 minus V2 is V out. So this is the switching function. S11 and the S21, if you use H11 plus H21, it should be equal to 1. So from here, you can see H11 is here, H21 is here, so H11 plus H21 equals to 1. So no problem. This line, H12 and plus H22 equal to 1. So H12 plus H22 equal to 1. So then we can calculate the output. The output is H11 multiplied by Vin minus H12 multiplied by Vin. So H11 here, H12 here. So H11 minus H12 equals here. And here we can get the negative. So here is 0, here is 1. So this is negative. So then 0 and then positive. So this is V out. So now we want to analyze this circuit. So how can we analyze this circuit? First, what is output? The V1 output is H11 Vin plus H21 0. So if you check this figure here, what is V1? V1 is H11 Vin plus H21 here, V0. How about V2? V2 is H12 Vin plus H22 V0. So we can easily calculate V1 and V2 according to the figure. So we have V1 equal to H11 Vin plus H21 0. V2 is H12 Vin plus H22 0. How about V12, which is V out? So we use this minus this. So H11 Vin minus H12 Vin. So here, H11 Vin minus H12 Vin. So we have the same Vin. So it is H11 minus H12, then multiplied by V in. So we can step by step calculate the output voltage. So how about the voltage across the switch? So first we want to show the first switch, VS11. So what is VS11? So we can go back here. What is VS11? Here, plus here. So V in minus V1, right? So V1 is here, V in is here. So H12, the voltage across H11 is equal to V in minus V1. Okay, so we can use very simple idea. We can compute VS11. So VS11 is V in minus V1. So what is V1? H11 V in plus H21 0. We just show this. So V in minus V1, so it is equal to here. So we can obtain the voltage across the switch S11 is here. How about the voltage across the S21? So now we want to learn what is the voltage across the S21. So where is S21? Here, S21. So it is this voltage. What is this voltage? 0 minus this voltage. 0 minus V1, right? So what is V1? V1 is H11 V in plus H21 0. Okay, so we can easily apply the same rule. So we can calculate S21. It is equal to 0 minus V1. V1 is H11 V in plus H21 0. This is V1. So this is ground 0. So we can get this voltage. So what is the voltage across the switch S21? It is negative, always negative. How about this one? This is 1 or 0. So V is always positive. So you can see this is always positive. How about this one? This is minus. H11 either 1 or 0. No negative. V is always positive. So this is always negative. How about S21? So we can calculate the voltage across S21. What is the voltage across S21? Here. It is equal to here. 0 minus V1. What is V1? H11 V in plus H21 0. So this is 0 minus V1. So now we calculate VS21. So we can calculate VS21. So it is 0 minus V1. What is V1? H1 V in plus H21 0. This is V1. 0 minus V1. So here. So what is the voltage across S21? Is it positive or negative? This is always positive. This is always positive. Positive, positive. This is always positive, but we have negative here. So this is always what? Negative. Okay. So how about VS12? So now we calculate S12. S12 is here. So this point is V in. This point, what is this point? This point is, we can see here, V2, right? So what is V2? V2 is H12 V in plus H22 0. So we can see it is V in minus V2. So VS12. So now we can see VS12 here. So VS12 here. So it is V1 out minus V2 out. But V1 out is H11 V in minus H12 V in. So it is here. So my question is it positive or negative? So you can see V is always positive, right? But we don't know H11 is 1 or 0. We don't know H12 is 1 or 0. So if this is 0, this is 1, it will become negative. If this is 1, this is 0, become positive. So there are two possibilities, right? So you can see the VS12 voltage. So by using the same way, we can calculate AV voltage across the switch. Then, how about the voltage ratio? We can calculate V out divided by V in. It is H11 minus H12. So do you think V out divided by V in is negative? Is it possible for negative? From here you can see if this is 1, this is 0, it could be negative. It also could be positive. If this is 1, this is 0, it is positive. So the output voltage could be positive, could be negative. If half positive, half negative, it becomes 0. So we have many possibilities. So S11 and S22 have duty cycle. If we set H11 equal to H22, half, then H21 is 1 minus H11, and the H12 is 1 minus H22. So we can see V out is H11 minus H12, but H12 plus H11 is equal to 1. So H12 is 1 minus H11, right? So we can use this one. So it is equal to 2H11 minus 1. So we already learned H11 has amplitude 1 divided by A. If duty cycle is 0.5, A is equal to 2, right? So we can say H11 is 1 divided by A. This is twice, so 2 divided by A. This is minus 1, copy, minus 1. So what is A? A could be 1, A could be 2, A could be 3, but A cannot be 0.5. A always larger than 1. So here, if A equal to 1, so 2 divided by 1 become 2. 2 minus 1 become what? 1. So if A is 2, if A is 1, what does this mean? Means S11 always turn on. So if S11 always turn on, then V out equal to V in, right? Equal, because H11 always on. If here, if H11 equal to 2, then what happens? 2 divided by 2 become what? 1. 1 minus 1 become what? 0. So if A equal to 2, which means H11 is half, right? H11 is half, and the H12 is also half. Half minus half become what? 0. So you have half positive, half negative. So what is the output? Equal to 0. So you can change A or you can change duty cycle to change the output ratio, or we call the gain of the output. So if A equal to 2 here, 2 divided by 2 become 1. 1 minus 1 becomes 0. Okay. If A equal to infinity, what does this mean? A equal to infinity, 1 divided by infinity become what? 0. So H11 is always 0. If H11 is always 0, then H12, then H11 is 0, H21 is 1, right? So then what happens? V out is equal to minus V in, okay? If A is 1, what does this mean? Here, 2 divided by 1 become 1. This is A is 1, 2 minus 1 become 1. So output is always the gain is always 1, which means V out equal to V in. So we can change the duty of the switch, then we can change the output voltage. We can obtain different gain. So by using the same way, we can develop V in divided by V out is 2 divided by M minus 1, or 2 divided by A minus 1. So A always larger than 1. If A equal to 2, then 2 divided by 2 become 1. 1 minus 1 becomes 0, which means the I in is always 0. Okay. If the M equal to 2, then what happens? 2 divided by 2, then this is 0. If M equal to 4, then 2 divided by 4, then this is minus 0.5. So we can change the gain of the current and the gain of the voltage. So for each switch, we can obtain the current is equal to output current multiplied by the duty cycle. So H11 is H11 I out, H21 is H21 I out, H12 is H12 minus I out, and H22 is I22 is H22 minus I out. So we can also develop the current relationship between each switch. So now we can make a conclusion for S11. What is the voltage? Because H11 either 1 or 0. If this is 1, then what is the voltage across VS11? 1 minus 1 becomes 0. So the voltage across S11 is 0. If this is 0, then the voltage across S11 is V in. So two choices, either V in or 0. So we can say the voltage across the switch S11 is always positive, never negative. Because if this is 1, it is 0. If this is 0, become positive. So the voltage across the switch either positive or 0. So if this voltage across the switch is positive or 0, what does this mean? If the current flow, then it becomes 0. If the current is 0, then we have plus minus, it becomes plus, right? So it could be turn on or turn off. If you turn off, then you have V in voltage. If you turn on, you have 0 voltage. So it is quite clear. How about current? Current S11, we have I11 current. It is equal to H11 I out. I out is always positive. H11 could be 1 or could be 0. If this is 1, then what happens? I11 is equal to I out. It is positive. If this is 0, then I11 is 0. So the current has two situations. One is equal to I out. So if this turn on, it is equal to I out. Or if you turn off, it is equal to 0. But never negative, right? Either 0 or positive. So what kind of switch should you choose? What kind of switch have 0 or positive voltage and 0 or positive current? What kind of switch? Transistor. If you turn on, then you have positive current flow. If you turn off, you have 0 current. If you turn on, then you have 0 voltage. If you turn off, you have positive voltage. So what is this device? Should be IGBT, MOSFET, or power transistor. You have 3 choices. How about S12? S12, we have voltage is equal to 1 minus H12 V in. If H12 is equal to 1, then we have 0 voltage. If H12 is equal to 0, then we have V in. So we have forward voltage blocking. So if you turn off, it have positive voltage. If you turn on, the voltage is 0. So 0 and positive. If you turn on, 0. If you turn off, plus minus, blocking voltage, right? How about current? Current is here. Minus H12 I out. I out is always positive. H12 equal to 1 or 0. So if this is 1, I12 is minus I out. What does this mean? If you turn on, then the current is negative, not positive, right? Negative. If you turn off, the current is 0. So what kind of device have negative current or 0 current and positive voltage or 0 voltage? What kind of device should be here? Diode. So you have to choose diode because you cannot choose IGBT. IGBT cannot be go this way. The current cannot flow this way, right? So if you have current go negative, but the voltage go positive, then it should be diode. So we choose S12 as diode. We choose S11 as transistor. So no problem. Then we can draw the H bridge. So what is the H bridge? So it is like this. So we have transistor here, and then we have diode here. So this way, or this way. We can go this way, or we can go. Sorry, we can go this way. This is wrong. Should be this way. This is wrong. Or we can go this way. Okay. So we have two choice. So we have S. Now we continue to S21. S21 voltage is minus H11 V in. So if this is 1, then S21 is negative. If this is 0, it is 0. So this is S21 either negative or 0. And how about current? Current either 0 or positive. So we have negative voltage blocking. So negative voltage blocking, but forward current carry. So this way. So what kind of device, when you turn off, it is positive, negative. And when you turn on, it go this way. So it is diode. So we can have, this is transistor, then this is diode. By using the same way, this is diode, this is transistor, because we have negative voltage blocking, so plus, minus, and a negative carrying current, so negative carrying current, negative blocking voltage, so we have to choose this. So now we have 1, 2, 3, 4, 4 switch, and we choose this 4 switch. So what is the final circuit? It will become this way. So we have, if we go this way, then go this way. So we can go this way. If this is turned off, this is turned off, we have output here. So it can go this way. Okay. So we can draw the final circuit. It is like this. This is output current. So it is go this way. And we have switch here. We have diode here. So this is the final circuit. So if we have turn on this one, and we have the current go this way. So it go from here to here, and go back here. Okay. So if you turn off here, and turn off here, now you have to keep the same current direction. So you still have output current go this way. Then how can you get the path? So you have go this way. So then you have to choose this way, go this way, and then you have this loop, right? So we can have this circuit. So which does this mean? We use 1, 2, 3, 4 device, and we have battery here. So we design here, we have diode here, we have motor here, then we have motor here, we have switch here, we have switch here. So if you want to get some voltage to the motor, then you can, the current is go this way. So if you want to get the current, so you can have S1, S2 turn on. So I can turn on S1 and S2. Then I can increase the current. So I can turn on S1, S2. Then how about I out current? I out current is increase, right? Increase. If I turn off S1 and S2, then what happens? We have D1 and D2 should turn on. Otherwise, we cannot keep the current. If D1 and D2 turn on, then what happens? So we have voltage here, then the current should be decreased. So then next time, you turn on S1, S2, the current increase again. Current increase again. If you turn on D1 and D2, then the current decrease again. So we can control the motor, and the motor always get positive current. So the motor only rotate in one direction because the voltage is either positive or zero, right? So can you design this circuit for a motorcycle? Can you use DC motor to drive a motorcycle by using this circuit? Okay or not okay? So how about, what do you think? Can motorcycle run another direction? It's always positive because you cannot see, right? So motorcycle only forward. Can motorcycle go back? No, you have to turn around. So can I design this circuit for a motorcycle? Yes, no problem. Can I design this circuit for electrical vehicle? You have to go back. Then you always go one direction. Then how can you go to your park space? You cannot do it, right? Can you design this for elevator? Only go up. Then you cannot go back. You have to go downstairs to walk back. Do you design this kind of elevator? No. So what is the advantage of this chip? But only for certain application. If you design this for MRT train, it could be okay, only forward. If you design this for motorcycle, it is okay, but it cannot be for electrical vehicle or elevator because only one direction. If you need two directions, what can you do? You have to design this circuit. Then you can go this way, you can go this way, so the current can go positive, the current can go negative, so you can go forward or backward. So we call this is 4 quadratic control. So we have 4 quadratic control, which means we can go this speed can go positive, speed can go negative. We can go positive brake, we can go negative grade. So we have 4 quadratic control. But for this only 2 quadratic control, we only go one direction. So this is the application for H-bridge. We can use the concept of matrix converter to design the H-bridge. So the final circuit is like this. So we can use this for elevator or for electrical vehicle by using DC motor. So we have give everybody the assignment. So we will make a conclusion for this chapter. So in this chapter, what do we learn? We learn switching function, right? So what is switching function? 1 or 0, right? So what is the general rule of switching function? KVL and KCL. So you have the voltage loop, you have the current loop, but you cannot short circuit your voltage source. You cannot open circuit your current sink. So there are several general rules. Then you can develop your own circuit. So we use matrix converter, but the matrix converter can be developed to DC, AC, AC, DC, and the H-bridge, right? And then we discuss the application of the switching function. We say it is very useful because the principle is very simple, but the application is very wide. We can use the switching function to every different energy conversion. So we can develop our own philosophy to design the power converter. So this is the end of this chapter, and the next chapter will be inverter, or we call it is DC to AC converter. So first we will watch a video to learn what is DC AC converter, what is the general idea of the DC AC converter. So three-phase inverter.
Today we'll talk about the three-phase inverter, and this is made up of 3 half bridges. We call each of them a pole, and we are going to look at how you go from one DC source to a 3-phase load.
DC
looking at the
3 AC.
different switch states and how those relate to the line-to-line voltages and also the line-to-neutral voltages of the load. So let's go through each of these states. It's going to take some time, but the important thing is to break each one down and go through one by one. So that's what we're going to do.
So the structure is like this.
Inverter. So you can see that we have
DC to AC to 3-phase AC.
labeled phase A, phase B, and phase C. They are connected to the DC input.
DC
and
input.
with 0 in between the two.
So this is
the full
0
DC
for the DC side,
we have those two
0
together.
for the AC side.
Then we have a 3-phase load, and this could be any load. Generally, they're going to have at least a small inductive component in it that is going to make the current need to continuously flow.
So current should be continuous. So inductive load.
The important voltages that we're going to look at are at the output, and we're going to look at the line-to-line voltages.
Line-to-line voltage.
We have
Line-to-line
down
voltage.
here, so that's looking at the voltage from VA to VB here.
VA,
And we
VB.
also put that in terms of line neutral values. So for example, VAN would be from
VA to VN. This is
the
phase.
neutral point of the load.
VA to VB is
Then we look
line.
at the line to
Line
line
voltage
voltages, so
and
it's
phase voltage.
VAB, VBC, and VCA. And then we'll also look at the line to neutral voltages, VAN, VBN, and VCA.
VAN, VBN,
The
VCN.
table in the upper left gives all of the possible combinations for each of these poles. So when you see
how many
positive,
pattern can
positive
you have?
VA, this means that the VA is connected to the positive
So
part of
VA
VC. So
means
if
this
you were
turn on.
to switch closed, switch S1 would be closed here. And so VA is connected to the positive
So
part.
VA is positive.
And
If this
the
is
next
turn
one,
on,
I'm just going to do the first row of this table. VB is also connected to the positive part, so we're going to have
so
this
if
switch
this
closed.
on, then VB is
And then the third
positive.
one, phase C is also connected to the positive here.
If this
So we're
turn
going
on,
to analyze each
and
of these
this is positive.
circuits to understand all of the different combinations.
So how many
on this
switches
table, there are 8 different combinations.
8 different
because each bit can only be in the positive or negative state, but then you have to take all the combination of those.
So total
We're gonna get
8
different states.
combination.
We're going to go through all of those just to see what does the line-to-line voltage look like in that case, and what does the line-to-neutral voltage look like for each of those. I'm always going to step us through each of these. We're going to start with the
So
first
this
row.
one,
And so this
copy
is what all
here,
of them
this one
are
copy
connected to the positive part of
so
the
if
DC.
turn on, turn on, turn on,
When you
it
rearrange
is like
this,
this.
you see this diagram down here. And we're just gonna label in here, we're just gonna put these, they're all the same, so it doesn't really
So
matter.
S1 on, S3
So
on,
this is what it
S5
would look
on.
like. And you can kind of tell from this one, they're not connected over any voltage. So actually everything in here is gonna be 0 volts.
So they are not
So
connected
we're
here.
gonna fill
So
in these tables.
We call this
The middle one
voltage
shows
is
the
0
line
because
voltages.
battery cannot flow.
AB, BC,
No phase.
BCA. And the one on the right shows the line to neutral voltages, VAN, VBN, and VCN. So we're going to go line by line and fill this in. Luckily, this is a very easy case, and we have the schematic at the bottom to help us. So we can see that the line-to-line voltages here are all going to be 0, 0, 0, and 0. Easy. And the line to neutral voltages are also going to be 0.
So in this case, 0
that's
voltage
The
because
first case, let's
they
go
short circuit each other.
to the next case. So let's just go one at a time. VA is now negative, meaning that
VA is
instead of
negative.
S1 being on,
It's on.
S4 is going to be on. And remember, only one switch in the half bridge can be on at one time. So we have that one connected. And then the
So
other
VA is
two,
here.
VB, connected to positive.
So
and
this is a
VC
positive.
is connected to positive. So
So
you can see this
positive,
connections
negative.
here. Let's rearrange that a little bit easier to
So
digest.
it is equal to here.
And so at the bottom you
This
see
is
the.
VA.
So based on the same ideal impedance, we can determine the voltage across these different loads. So you'll see B and C are in parallel, meaning
So
their
B and C
are
in
so
parallel.
they're halved.
So
While
They
the
occupy
A
half.
here is
1/3.
by itself.
This is
So-
twice 2/3.
You're having half of Z in series with the full Z. And
So
if
this
you
is a
do
half
the math on that,
Z. This is full
you see
Z.
the voltage drop across the first two, so B and C here is 1/3 of B and
This is
C.
1/3.
While
This is
the voltage drop
2/3.
over the bottom one, bottom impedance, is going to be 2/3 VBC. So I want to keep that in mind as we look at the different voltages. So let's fill in this table again. First, we'll look at the line-to-line
If
voltages.
all
And
of
we'll
them
go one at a time. So
Turn
V,
to positive.
A,
It is
B.
0
So
voltage.
this is from A down here to B, and actually that's a negative VBC that we're going to see. All right, then we have VBC from the point B to here. That's going to be 0. That's just straight connected. Then we have VCA. So from here and to back to A. And that's going to be the positive VBC. Okay, so now let's go to the
In this case,
line to
we can
neutral
copy here.
voltages. We have them already drawn at the bottom so you can reference, but VAN, so from A to N, we're going to get 2/3 VDC, and the polarity is actually negative, so
This
it's
is
going to be
VAN
negative 2/3
2/3. But A is here, N is here, become minus
Let's look at
third.
VBN. So we're going from
So
this B to
VBN,
the line neutral.
1/3
And
positive.
that's going to be a
This is
positive
neutral.
1/3.
This is
BC.
1/3.
And then we're going to do the third one, which is from C
C to
to the
N,
line neutral, and that's going to
1/3
be
positive.
1/3 BDC. So Valerie will take us to the next one. Same sequence again. VA is positive, so we can draw switches here.
A
And
is
B
positive.
is negative, draw switch in here. VC is
B is
positive,
negative.
so we're drawing in these switches.
This is positive.
If we reconfigure this,
Then we can draw
it
this
looks
one.
like this, because two are connected to the
So
positive
A and
one is connected to
C
the negative.
positive.
Just like
A and
that,
C
just like that.
positive. B
But now let's
negative.
just name these phases in the diagram below. So A now is a positive,
So
so
A
we
is
can
here,
put that in this
positive.
box, this impedance. And this time B is in the
A
connected to the negative of the DC.
Is
So
positive.
that's gonna be B, and then C is going to be the
C is here, negative.
Okay, so you can see, again, we have that same structure of two in parallel on the top,
Two
they're connected to
parallel
neutral, and then
on the top.
one in series connected
In
negative
series
to
to
DC.
this one.
So you can see those voltages that we're going to get over each of them. Let's break this down again in our line to line and our line to neutrals. So once you have the diagram at the bottom, you just kind of fill it in. So from VAB, we have a positive VDC.
So VAB
Then
positive.
from a B to C, so now from here to B to C.
B
This
to
time it's
C, B
so
to
this
C,
time it's
negative.
negative VDC. And then from C to A, those are directly connected, so that's 0 volts. Then let's look at the line to neutrals. VAN is from this point to the line neutral. That's going to
VAN.
be positive
So 1/3
1/3.
positive.
VDC. Then we're going to have the B,
B,
and
and
this is
negative.
It's going to be the negative
2/3.
VDC, 2/3 VDC. And the last one, C to N is going to
C
be
to N.
positive 1/3
1/3 positive.
VDC.
Okay.
Now we're looking at the fourth row. So VA is positive, so that's connected here, S1 is on. VB is positive, S3 is on. VC, negative, so S5 is on here. Again, we can rearrange this to make it a little bit clearer. So at the bottom, you can see that here. And let's just write in the phases. So A and B are now connected to the positive, so A and B. And C is the one connected to the negative. And we're getting the same voltages, 1/3 VDC over the A and B, and then the 2/3 VDC over C. So let's fill in the tables. For VAB, so this is from this A point to B, which is over here, we're going to get 0. And then from VBC, we are going to get from BC, we're seeing positive VDC there, so VDC. And then from C to A, so from bottom to A, we are getting a negative VDC.
So we can
Okay,
have
let's look at
20
the
minutes
line
break
control.
and we will continue for the video next class.